Hello guys, welcome to today's class on fluid mechanics. So in today's class, we are going to be talking about buoyancy and flotation. Now we all know that whenever an object is immersed completely or partially in a fluid, that object always experiences an upward force which tends to pull it out of the fluid. That upward force is simply called a buoyant force. And this buoyant force can be determined from Archimedes' principle, which states that when a body is completely or partially immersed in a fluid, it experiences an upward force which equals the weight of the fluid displaced by the body. Now, this upward force is called a buoyant force. So, if we submerge a body inside a water, let's say we have a vessel containing water. Okay, let's say we have a vessel containing water and then we submerge an object inside this vessel. We submerge an object inside this vessel. This object moves down in the direction of gravity. That's simply the weight of the object, and that's equal to mass times gravity. From Archimedes' principle, it simply says that whenever this object or an object is immersed in a fluid, what happens is that this object experiences an upward force simply called the buoyant force. So this upward force is simply called buoyant force. Okay, so we use FB, F subscript B to represent buoyant force. And this buoyant force is equal to the weight of the fluid displaced by the object. The weight of the fluid displaced by the object. So from Archimedes' principle, the buoyant force, FB, is simply equal to what? Weight, which is mass times gravity. Now, what Archimedes' principle is saying is simply that whenever an object is immersed in a fluid, the weight of the object in air, that is under gravitational condition, is equal to the weight of the object, is equal to the weight of the fluid displaced by the object when immersed in water. So we have two conditions: weight in air equals weight in water. Okay, so we have two conditions. The weight of the object in air is equal to the weight of the fluid or water displaced by the object. So weight in air equals weight in water. Now, from the idea of what we've said so far, it means that one thing is very, very important whenever talking about buoyancy and flotation, and that is simply what? The weight of the object is a very important factor talking about buoyancy and flotation. The weight of the object is a very, very important factor. Now, considering the weight, three things actually happens. Considering the weight of this object or the weight of every object immersed in a fluid, three things actually happens. First, or one, when the weight of the object is greater than the weight of fluid, when the weight of the object is greater than the weight of the fluid which the object is actually submerged into, what happens is that the object sinks. So when weight of object is greater than the weight of the fluid, what happens is that the object actually what? Sinks into the water. It sinks to the bottom of the water. Whenever the weight of the object is greater than the weight of fluid, the object sinks. Second thing that happens is that whenever the weight of the object is equal to the weight of the water, what happens is simply that the object floats on the water. That is the case of when you place a rubber on an ocean, a plastic or a rubber on an ocean. What happens is that you notice that that plastic or that rubber actually floats on the ocean simply because the weight of the rubber at the portion of the ocean in which the rubber is submerged is equal to the weight of the fluid displaced by that rubber. So the two of them have equal weight. The rubber actually floats. In the case of the first condition, if the weight of the object is greater than the weight of water or the weight of the fluid, the object sinks. That is the case of a stone or a metal. If you put a stone or a metal into a water or into an ocean, what happens is that the stone actually sinks straight into the bottom of the ocean. Why? Because the stone has a higher weight, or you can say is more dense than the water. All right, so second condition, whenever the weight of the object is equal to the weight of fluid, we have flotation. Okay, we have flotation. So if the weight of the object equals the weight of the fluid, the object is said to float. Finally, if the weight of the object is less than the weight of the fluid, if the weight of the object is less than the weight of the fluid, what happens is that the object will have some portion of its body submerged in the water, Meanwhile, some portion of its body actually floating. Okay, so when the weight of object is less than weight of fluid, okay, the object will have some portion submerged in water and some, okay, floating. All right, so that is as a result of a wood. If you carry a plywood and throw into water, you notice that, let's call this a plywood. You throw this plywood inside water. What happens is that some portion of this plywood is actually what? Let's say this is water and this is water. So we have some portion of this plywood actually what? Submerged in the water. Meanwhile, some portion from here to this point, as can be seen, okay, actually floating. So that's the case of a wood. If you throw a wood or a plywood into a river or an ocean, what happens is that some portion of that plywood is submerged, while some portion of the plywood is actually what? Floating. That's simply because the weight of the object is less than the weight of the fluid. So these are three conditions that play around what, considering the weight of every object and what causes buoyancy. Now, Archimedes' principle said that, for a body that is fully submerged in water or partially submerged in water, the weight of that object in air is equal to the weight of the fluid displaced by that object. So that means for this particular given object, we have weight of the object in air and weight of the object in the water. Sorry. All right, so let's consider that, okay, this is water and this is the object submerged in water. So this is when the object is in water, okay, object in water. Let's consider this to be a case when the object is in water, and then let's consider this to be a case when the object is actually not submerged yet in water. So this is simply saying object in air, okay, when the object is in air. All right, now if this object is in air and of course this is the object in water, now let's explain what Archimedes' principle actually says. In air, we consider this to be the depth of the object. This is the depth of the object, and this is the length of this object. This represents the length of the object, L. And let's say if we draw an isometric view of this object, okay, kind of a three-dimensional view of the object, we are going to have this to be the width of the object. Call this W. That becomes the width of the object. So let's divide here a bit. So that becomes the width of the object. So in air, this is the condition of this object now in air. This is the depth of the object, this is the length of the object, and this is the width of the object. Having known these parameters, it means we can find the volume of this object in air. All right, so obtaining the volume of the object in air, volume of object in air, okay, so simply call that V air, and that's equal to what? The length times the width times the depth. That gives us the volume. Length times width times depth. This gives us the volume of the object in air. But let's consider in this case when the object is submerged in water. What happens is that since the weight of this object is less than the weight of the fluid, or water in this case, we've said some portion of the object is what? Submerged. So which means in the water, the body actually has a new height. So this is now the height of the object or a new depth. This is now the depth of the object in water. So simply use H. Let's use small letter H to represent the depth of this object in water. Meanwhile, depth in air is actually from this portion to this portion, okay, which is simply from here. We call that D. From here to here represent the depth in air, okay. We call that capital D. But now, when this object is submerged in water, we have some portion of it floating. So this remains now the height of this object in water. Now, if we do an isometric view of the object just like we did in the first case, okay, we also have that in water, the length remains the same, unchanged. Also, in water, the width also remains unchanged, probably. The only thing that changed when this object is submerged in water is now what? The height. The height changes. Therefore, you can now obtain a new volume of this object in water. A new volume of the object in water. So this becomes volume of object or volume of water displaced by object. Volume of water displaced by the object, simply call that VW, volume of water, and that is simply equal to the length times the width times, now we simply use this for the depth, h, the height or the depth of object in water. This becomes the volume of the object in water. Now, if we know the volumes, now from Archimedes' principle, we say weight of object in air is equal to weight of object in water. So all we need to do is simply what? Obtain the weight of this object in air, obtain the weight of the object in water. And in our previous classes on fluid mechanics, so please do well to look up the introductory video for proper understanding. In that video, I explained what specific gravity is as simply the specific weight of every object divided by specific weight of water. So from there, we can be able to find the specific weight of every object since the specific weight of water is a constant value, 9.81 kilonewtons per meter cube, or simply 9810 newtons per meter cube. Okay, and if we know the specific gravity of every object, that will help us to find the specific weight of the object. And I also said specific weight simply means weight divided by volume. So if specific weight is weight divided by volume, it means we can find the value of the total weight as simply specific weight times volume. Let's do that now in this explanation and see. Now, the whole aim of this whole idea is to obtain the weight of object in air, obtain the weight of object in water, or let's say fluid in this case. All right. Now, recall we said specific gravity, S dot G, specific gravity, which we simply use our capital S to symbolize. We said it is the specific weight of every object all over specific weight of water. This is what gives us specific gravity. And I said from here, if we make specific weight subject of a formula, specific weight of the object becomes specific gravity times specific weight of water. Okay, if we simply make WO, which is specific weight of the object subject, we are simply going to obtain that specific weight of the object is simply what? The specific gravity multiplied by specific weight of water. And specific weight of water is constant, where WW, okay, where specific weight of water is simply what? 9810 newtons per meter cube. So if we're able to obtain, if we know the specific gravity of this object and we know the specific weight of water to be 9810, it means we can compute the specific weight of the object to be this. So it means now that specific weight of object, WO is simply equal to, we said the specific gravity multiplies specific weight of water, okay, which is 9810. Okay, this gives us the specific weight of water. And also, specific weight, okay, mathematically, what it means, or specific weight of the object is now equal to the actual weight of the object divided by volume. And the unit we said is simply newtons per meter cube because the unit of weight is newtons, unit of volume is meter cube. So specific weight of object is simply the weight of the object divided by what? The volume. So this means that in order for us to obtain the actual weight of the object, we have to simply what? Cross multiply. Specific weight of that object multiplied by volume. That gives us the actual weight of the object. Therefore, weight of object WO is simply equal to specific weight of object multiplied by what? Volume. And we've said that the weight, the volume of the object in air gave us this length times width times depth. So if we know the volume of object in air, it means that we can actually find the weight of object in air. Weight of object in air is simply specific weight of object multiplied by volume of object in air. And the value is in newtons. So this is how you obtain the weight of every object measured in air. Now, in the aspect of fluid, let's say this fluid, let's now assume that this fluid is water. Having known the volume of this object, or the volume of water displaced, or volume of fluid displaced by the object to be this. Therefore, if this is water, we know the volume of water displaced by the object to be this. Therefore, specific weight of water is a constant value. Okay, specific weight of water, this one is known, okay, as simply 9810 newtons per meter cube. This is the specific weight of water. If we know the specific weight of water, it means we can actually find the weight of water displaced by the object. If we know the specific weight of water and we know the volume of object in water, then multiplying the two of them together, just like we did here, specific weight of object multiplies volume of object in air gives us the actual weight of the object in air. Therefore, to obtain the weight of the object in water, weight of object in water, or weight of water displaced by object by the object, so simply call that weight of water. Okay, and this is now equal to specific weight of water multiplied by what? Volume of water displaced by that object. And of course, we know the specific weight of water as 9810. Okay, so this multiplies by volume of object displaced by the water. Volume of water displaced by the object, sorry. So we simply have this. Now, Archimedes' principle is simply saying that these two weights are equal. The weight of object in air is simply equal to the weight of water displaced by the object. Okay, so these two weights from Archimedes' principle are equal. So you simply have from Archimedes' principle, you now obtain that weight of object in air, specific weight of object in air, multiplied by volume of object in air is simply equal to what? Specific weight of water, okay, multiplied by volume of water. So you simply have this equation. So, all right, so from here, if you put in the actual formulas into this equation, we simply have specific weight of object multiplied by the volume of object in air is simply length times width times depth, okay, and this is equal to specific weight of water, which is constant, 9810 multiplied by volume of water displaced by the object, and that is simply length multiplied by width multiplied by, now the depth becomes depth of object in water, it is simply h. So you have this. So this is all the Archimedes principle is saying. The weight of object in air equals the weight of objects immersed in the fluid. Now, there are other things to talk about considering this object in air and considering the object in water. All right, so considering the depth of object in air and the depth of object in water, we have what is called the center of buoyancy and the center of gravity. Center of gravity and the center of buoyancy. Okay, considering the height or the depth of object in air and in fluid, we have the center of gravity and the center of buoyancy. Now, the center of gravity is that point where the entire weight of every object acts when it is under atmospheric condition. The center of gravity is that point where the entire weight of every object acts when it is under atmospheric condition, and it is actually or usually found at the middle of the depth of every object. It is found at the middle of the depth of every object in air. So under atmospheric condition, the middle of the depth, okay, let's try to get this. So the middle of the depth, this is called the center of gravity. The middle of the depth is simply called, or is a point where the center of gravity acts. So center of gravity, simply C dot G, C dot G is simply equal to the depth all over the 2. The center of gravity is usually found at the middle of the depth. So it's simply given a depth all over 2. Whereas center of buoyancy is the point where the entire weight of every object is found when the object is immersed in a fluid. So take note between the two differences. In center of gravity, the object is under atmospheric condition, but in buoyancy, the object must be immersed in a fluid. Now, the point where the entire weight of the object acts when the object is immersed in a fluid is called the center of buoyancy, and it is found at the center or the middle of the depth of the object when immersed in fluid. So if this is depth of the object in the fluid, of course, if we trace this line and of course divide this into 2, this becomes the center of buoyancy, the center of the depth of the object immersed in the fluid. Therefore, center of buoyancy, CB, is simply what? H all over 2. This gives us the center of buoyancy. All right, so we've talked about flotation, we've talked about Archimedes principle, and of course, if you want to talk about the laws of flotation, they still boil down to Archimedes principle. And of course, we have to actually have two laws of flotation, and they all still center around the Archimedes principle. The first law of flotation is actually gotten from the Archimedes principle, which states that every object immersed in the fluid, completely or partially, has the same buoyant force as the weight of the object. That's the first law of flotation. And the second law of flotation states that every object immersed in a fluid displaces its own weight of the fluid immersed in. Every object immersed in a fluid displaces its own weight of the fluid it is immersed in. That's the second law. So the both of them actually boils around Archimedes' principle. All right, guys. So let's consider this problem to actually follow up our previous explanation on buoyancy and flotation. Consider this question on the board. The question says a wooden block of width 2.5 meter, depth 1.5 meter, and length 6 meter and length 6 meters is floating horizontally in water. Please take note, in water. If the specific gravity of block is 0.65, question says 1. Find the volume of water displaced. 2. The position of center of buoyancy. So I'm still going to use the previous analysis to actually explain this question. So let's have this object on air. So simply object in air under atmospheric condition. So we have this object, okay? We have the object. Let's use a three-dimensional view to indicate this. So we're given the length of this object. Length of the object was given in the question. Length of block is 6 meters. So the length is simply 6 meters. The depth of this object was given. Depth or simply height under atmospheric condition. The depth was given as 1.5 meters. So depth is 1.5 meters. And then the width of the object was given as 2.5. So we have the width of the object given here as 2.5 meters. All right, so we simply have it. This is when this object is under atmospheric condition. Now, the question says, if the object is submerged in water, okay, is floating horizontally in water. So this object now floats inside water. So object in water, let's do that over here. Object in water. All right, so we have the object now in water. Let's also do an isometric view of it in water. So we have this. The length of object in water remains unchanged, is 6 meters. The width of object in water also remains unchanged, it is 2.5 meters. Now, this is now, of course, in water, part of the object floats. From the question is even clear there. They say an object is floating, so part of it floats, meanwhile part of the object sinks in water. Okay, so we now said under this condition, it means we have a new depth inside the water, and this new depth is unknown. So we simply call this h. So you can simply use small letter h to represent the depth of the object in water. So this is the object. This is when the object is in air, and this is condition of the object in water. So we simply have this. All right. Now, having known once again, if we go through the equation, we were given the specific gravity of block. Specific gravity of block is 0.65. So not forgetting that specific gravity, okay, of block S equals 0.65. So we are asked to find the volume of water displaced by the block and of course the position of center of buoyancy. Now, in order to do this, we need to first of all find from Archimedes' principle what is the weight of this object in air and what is the weight of this object in water. That's all we need to do because from Archimedes' principle, the weight of object in air equals the weight of water displaced by this object. Okay, now in order to do that, first of all, we compute the volume of the object in air. All right, volume in air. So simply use V air to represent that. We said it simply was the length times the depth times the width. That gives us the volume of the object. Length is 6 meters, so we have 6 multiplied by the depth is 1.5 multiplied by the width is 2.5. And if we do this simply gives us volume of block in air is simply equal to 22.5 meter cube. So this becomes the volume of the object in air. Okay, just as we've done here, next thing is for us to obtain the volume of the object in water. Now, volume of object in water, okay, volume of block in water, okay, simply use VW, and that's equal to also the length times the width, now times the new depth, which is simply represented here by what? H. So we have length is 6 meters, depth is H, and of course the width is 2.5. So we have this. So this implies that the volume of water displaced by the object is simply 6 times 2.5 H. That gives us 15 H in meter cube. So this becomes the volume of the object in the water, and this becomes the volume of object in air. Now, having known these volumes, next thing to do is to what? Obtain the specific weight of this object in air. Obtain the specific weight. We are given the specific gravity of the object, so we can simply use that equation, find the specific weight. Use that condition and find the specific weight of this object in air. Okay? Now, we know that, recall, specific gravity S, we said is simply specific weight of object or block in this case all over specific weight of water. And we know that specific weight of water is a constant value, 9810 newtons per meter cube. So we simply make the specific weight of the object or block subject to a formula. Therefore, specific weight of block, okay, WO is now equal to specific gravity multiplied by specific weight of water. It's as simple as this. Therefore, specific weight of block is now equal to specific gravity of block was given as 0.65. So we simply have 0.65 multiplied specific weight of water is constant 9810. So this value will give us 0.65 multiplies 9810. So this gives us 6380 in newtons per meter cube. Now, this is now a specific weight measured in newtons per meter cube. So we can now obtain the actual weight of this object in air by simply what? Multiplying this object specific weight towards the volume of the object in air. If we do that, the meter cube cancels out. We now have the actual weight of the object. Therefore, actual weight of object in air simply WO is now equal to specific weight of object multiplied by what? Volume. And okay, volume in air, this is now equal to the specific weight of the object we obtain to be this 6380. So we have 6380 multiplied by the volume of the object in air gave us 22.5. So multiply by 22 0.5. Now, this simply means that the weight of this object in air, okay, is now equal to 6380 multiplied 22.5. That simply gives us 143,550 Newton. Okay, this gives us the weight of the object in air. Now, we know the weight of object in air. The next thing to do is also use the same approach to compute the weight of the object in the fluid. Now, to obtain the weight of object in fluid, this fluid was given as water, not forgetting in the question, it was given as water. And we know that specific weight of water is constant, 9810, okay? So, specific weight of water, okay, WW is simply 9810 newtons per meter cube. So we already know the specific weight of water. Since we know the specific weight, it is simply now to obtain the total weight of water or the object in the water. It's simply by multiplying this specific weight of water to what? The volume of object in water. This will now give us the weight of the object in the water. It will give us the weight of the object in water. All right, so let's do that over here. So since we know specific weight of water, okay, specific weight of water, okay, WW is the same thing as total weight of water all over volume of water. Okay, so it becomes total weight of object in the water divided by volume of the object in the water. So we can now find total weight of objects in water. Therefore, actual weight of object in water, okay, capital W now is now equal to what? Simply cross multiply. It becomes volume of object in water multiplied by specific weight of water. So we simply have volume of object in water multiplied specific weight of water. This is now equal to the volume of the object in water. We obtain that value to be what? 15H. So we simply have here 15H multiplied by specific weight of water is constant 9810. So if we multiply this together, 15 multiplies 9810 will give us. Therefore, the actual weight of block in water gives us 147150 in 50H. Please, not forgetting 50H in newtons, okay? Because there's a H attached here, so don't forget that. So from Archimedes principle, okay, we have that the weight of the object in air, is equal to weight in water. So this simply implies that the weight of the object in air, we obtain that value to be this 143550. So this implies 143550 is equal to the weight of the object in water, which is 147150 H. So from here, we can now be able to determine the height of the object in the water. So if we make H subject there, this simply means height of object in water, which is simply H, is equal to, okay, 143550, 143550 divided by 147150, 147,150. So this simply implies that the height of the object in water is 0.98 meters. So this becomes the height of the object in water. The first question says calculate the volume of water displaced. So of course we know the volume of water displaced. Recall volume of VW is equal to the length of the object remains constant, the width of the object remains constant, but now the depth becomes depth of the object in the water, which is simply what? H in this case. Therefore, this implies volume of water displaced by the object is now equal to length of the object is 6 meters, width of the object was given as 2.5, and then the depth in water is simply H, which is given here as 0.98. And if you evaluate this, you're going to obtain the volume of the object in water to be 14.7 meters cubed. So this becomes the volume of the object displaced. The next question says we should find the center of buoyancy, the position of center of buoyancy. And I said earlier that center of buoyancy, CB, is simply equal to what? The depth of the object in water divided by 2. So this is now equal to the depth of the object in water gave us 0.98. So we simply have 0.98 divided by 2. And this is equal to 0.49 in meter. This becomes the center of buoyancy. Alright guys, so I hope you find this video very helpful and self-explanatory. Please, if you do, don't forget to leave your thoughts in the comment section. And of course, if you have any questions at all to ask, you can do that as well in the comment section, or you come to my DM on WhatsApp and I promise to respond to all your questions. Thanks guys for this wonderful question. I will see you in the next video with more amazing questions on buoyancy and of course laws of flotation. Thanks.